Hello and welcome. This is a supplemental recording on symmetry and group theory that we didn't get to in class. So pulling up the slide here. Oh, is there a way to make this full screen? Um, side-by-side speaker, side-by-side gallery. There we go. Cool. Okay. So sorry for the delay. Still getting used to the presentation format. Um, so here are notes on symmetries, starting with a poem about symmetry by William Blake. Although in order for the poem to rhyme, you have to say it the way they said it in Blake's time, which goes, tiger, tiger, burning bright in the forests of the night. What immortal hand or eye could frame thy fearful symmetry? In what distant deeps or skies burnt the fire in thine eyes? On what wings dare he aspire? What the hand dare seize the fire? And what shoulder and what art could twist the sinews of thy heart? And when thy heart began to beat, what dread hand, what dread feet? What the hammer, what the chain, in what furnace was thy brain? What the anvil, what dread grasp dare its deadly terrors clasp? When the stars threw down their spears and watered heaven with their tears, did he smile to work to see? Did he who made the lamb make thee? Tiger, tiger, burning bright in the forests of the night, what immortal hand or eye dare frame thy fearful symmetry? So what is symmetry? What is symmetry? There, there are two classes shown here. Although since I'm at home, I can show you a couple of examples first that aren't quite talked about much here. So I'll give you my own spin on it instead of uh, following these notes verbatim. Um, so symmetry, generally speaking, is a way to rearrange the objects in a set, but in a way that preserves the structure of that set. And we can define that concretely based on what the structure is, and we'll go through examples, but I want to start with some intuition that you can see here in the camera. So here I have a cube, and you can see a cube here. And if I said, hey, look over there, and you looked, and I moved it like this, um, maybe you could see the color change, but if you ignored color, what I've done is a symmetry because I've rearranged the points, but it's in a way that you can't really tell. And I also haven't ripped the square apart, the cube. I haven't ripped the cube apart or destroyed its structure in any way. So motions of objects that have some kind of inherent symmetry are great examples. If you pay attention to color, I couldn't trick you by replacing a green side with a blue side, but if these were all the same color, then um, then you could imagine moving that object through space. Um, here's another example. This is an icosahedron, has 20 equilateral triangles on its side. And if I were to even taking into account color, yeah, there's the camera. Even taking into account color, if I were to take this edge right here and rotate it 1/5 of a turn, right? Even with color taken into account, you wouldn't be able to tell unless you saw me turn it that I had turned this object. So we have this nice rotational symmetry for this object where you can see 5 different positions, all indistinguishable from the original starting spot. Um, and this doesn't have to be just for three-dimensional shapes. They just make great examples. So you could also, and we'll get to this in a moment, but even just a triangle on the plane, rotating a triangle, that is a symmetry. I'm moving the points through space. And if I were to even reflect it up, you can see the color changed. But if we ignore the color and just think of this as a prop and ignore color for a moment, then we can see more of the full symmetry possible in these shapes. And something like this, if we don't insist that the colors match, then we can have all kinds of arrangements of the shape. In fact, I can take any vertex to any other vertex in any way I like, and then rearrange the rest around that in one of 5 positions, or another 5 if you were able to pull it apart kind of from the inside and move it back together. But we'd need a 4th dimension for that. Um, sorry, we need a 4th dimension to rotate that through space without taking it apart. One more neat example is the dodecahedron. There are 2 other platonic solids that I didn't have enough triangles to pre-build before recording this, but here's another one. And at each vertex, I could do a third of a turn here. You'd have to ignore colors, of course, but there you go. There's some examples. And another interesting example comes from a Rubik's Cube. I have a cube that I could, again, ignoring colors, I could turn through space. The colors actually help us keep track of what we've done to the shape, which is nice. But in a pure symmetry sense for these objects in space, we wouldn't color these to highlight the fact that the positions are interchangeable for these different parts. So this yellow face right here could be replaced by the blue face, etc. But Rubik's cubes have even more things going on with it, such as turning aside and all of the intricate things that follow from those turns that can come from that. And something that's interesting about studying symmetry is that way is that if we just talk about symmetry as arrangements of things that don't destroy the structure, then we don't have a very good way to describe all of the ways to scramble a Rubik's cube, because we don't have a very good way to talk about the ways to either scramble up or unscramble a Rubik's cube generated by these terms specifically. That's a notion that you define in a group theory class called a subgroup, much like a subspace is a smaller space living inside a larger one. And when you study linear algebra, a subgroup is a smaller set of symmetries that live inside a larger one. But it's kind of hard to define that without a more robust mathematical looking definition. So we'll go into more examples, but hopefully this helps you motivate this subgroup of rearrangements of a Rubik's Cube you can accomplish without actually taking it apart and putting all the pieces together, the ones that you can actually generate by the rotations. Those are a notion we need to capture with a sense of subgroup, and that requires us to have a more robust and stronger definition. But it turns out with some work, you can prove that at least up to very, very close, you can recreate all of the sense of symmetry with that robust definition. So going down in the notes here. Oh, sorry, there was an example. 2 cases shown below with no structure. Sets actually have a symmetry to themselves. And it's all of the rearrangements, because if we're looking at just a set with no structure, there's no structure that needs to be preserved. So you can rearrange a set in any way you like, and that still counts as a symmetry because there's nothing you could possibly violate with your rearrangement. But if we're talking about, say, movements of the plane, like the triangle that I talked about a moment ago, this triangle rotating through space, that's a more interesting case because our angles and our lengths, they have to be preserved. And again, we're talking about the whole plane. So things such as, let me highlight this as I'm talking about it. Things such as reflections, rotations, translations, and glide reflections are the other compositions of the other things generated by reflections that aren't on this list. These are all ways to take the plane and move the plane around in a way that's preserving length and angle, which are the properties we care about. And in fact, when you study congruence in geometry, 2 shapes are congruent going all the way back to the way this is defined by Euclid as being able to pick up one shape and place it perfectly on top of another. Or maybe my favorite way of rephrasing that is you have two different triangles that are congruent, mouse slip, two different triangles that are congruent in space if I can say, hey, look over there, and then put this triangle on top of the other one in a theoretically perfect way. But all those SAS and ASA and SSS tests that you usually memorize in high school geometry, they're really congruence tests, and they're testing that property of congruence. And another example of congruence here, excuse me, is or no, sorry, not another congruence test. Another example of congruence is the integers. So if you are talking about the integers mod 12, let's say, two integers are congruent mod 12 if strictly defined, they're congruence mod 12 if their difference is a multiple of 12, an integer multiple of 12. But another way of saying that is we have these translations of the number line that come in 12s. And if there's one of those that moves one point onto the other, then we would say that they're congruent. So our symmetries or movements of the number line are only the ones that come in whole 12s, whole steps of 12. But if we look at this number line down here compared to this number line up here, right, you can see that it's shifted over. We've taken 36 and we've moved it all the way down to 12, and that movement was a multiple of 12. And here we have a photo. Comes from it comes from Hatcher. It was a beautiful. It was a covering picture, but the idea illustrated is really nice. You take the integers and you roll them up into a helix, and now that movement that comes in 12s can also be interpreted as one whole turn of the helix or multiple whole turns of the helix, just kind of like the way the hand of a clock moves around and repeats every 12. You have that repetition. So we can see all of the things in the same congruence class, or all of the congruent integers are on top of each other and with the same color, like these or these, for example. It's kind of, I thought that was neat, so I wanted to include that as a picture. So much like, I'm just going to read what I wrote here. Much like other aspects of mathematics, key properties of symmetries play a huge role in their study. In fact, the three properties below turn out to develop all of the other properties of symmetry as well. So we're going to establish three properties, and then, as is often done in mathematics, if the properties you found about something that you know are strong enough, if they do enough to capture the structure of what you're studying, then it's a safe bet to let go of everything else and keep only those properties as your definition. And then everything else that has those same properties can also fit that definition. And every result that you can leverage from those properties has to follow for everything that matches those definitions. And that's what we're doing with the group. So the examples of symmetries involving movement that you saw, or Rubik's Cube turns or rearrangements of the sides of a Rubik's Cube, those are all symmetries, but we're going to look at three really important properties of these symmetries. They're not just properties of permutations, they're properties of permutations that preserve structure in all of those examples. So first of all, symmetries are associative. Why are they associative? They are associative because function composition is associative. If you remember that these are permutations, so they're all invertible functions from sets to themselves. I have, let's imagine F and G are symmetries on my set. So these are invertible functions from a set to itself. That preserves structure. I need three functions for associativity. Excuse me. F, G, and H. So these are all functions from a set to itself. And then the composition, which means do one symmetry and then do another symmetry and then another symmetry. So for example, if I had a, you know what? Yeah. The Rubik's Cube's better, but it's all messed up, and I don't want to mess it up anymore. So if I have a cube here, and I turn the cube this way, and then I turn it that way, the resulting position you see is from the composition of those two. I've gone here and then here, and that is the composition. It means do the first function and then the next. Or in our case, do the first symmetry and then the next. So function composition, as we proved in class, is associative. So if we do F and then G and then H, this might not be well defined. If I were to say, stick these all together, do this, then this, then this. If these are just kind of abstract symbols that we put together, they may not be associative. And that might seem unbelievable, but if I do something like this, exponentiation, 3 to the 3 to the 3, this isn't well defined. There's a convention that people go with that kind of is meant to address this, but this, strictly speaking, is not well defined. If I were to do 3 to the 3 and then take that to the third power, that would not be the same thing as 3 to the 3 to the 3. These are not equal. These are not equal quantities. So one thing we'd like to check when we're going to do things repeatedly, when we're going to connect chains of things together, such as symmetry, is we want to make sure that if I were to compose the first two and then compose the last, then that's the same thing as composing the last two after the first. So to make sure that these things are in fact equal. And they are, as you know, from this property of functions. So these are associative, and we want to keep that property for anything we're going to call a group in general. We also want to make sure there's an identity. I maybe haven't mentioned this, but an identity counts as a symmetry, especially if we're going to compose symmetries together. If I mix up a Rubik's Cube, I want to also compose it with the fixing of that Rubik's Cube. I want to figure out how to undo that. So by looking carefully at that. Ooh, yay, just a half rotation. Okay, right, there's a way to return that and restore it to the position it started in. And the result of mixing up and then unmixing up a Rubik's Cube should be the state in which it started, and that is the function that does nothing. It just sends everything back to itself. It checks the ID of an element and says, yes, you're you. Come on in. So we want to make sure the identity function is included in any group to be able to talk to getting back to the start or unscrambling or undoing things. So the identity, again, having an identity is a very important property. And then finally, an inverse needs to exist for every element. So for every way we can rearrange the things in our set that doesn't that doesn't violate whatever the structure is that we care about on our set, doing the opposite or undoing that thing should also not violate the structure of our set. And of course, we're only talking about permutations, so they're all invertible functions, but their inverses in particular always preserve the structure as well. So going on, here are the abstract definitions of a group. So a group is a set. Maybe think of a set of symmetries, but it's abstractly, it's any set with a binary operation that takes pairs of elements in your group and returns another pair. And this is always meant to model some kind of function composition. It's always meant to model some kind of composition. So keep function composition in mind, but since we're going to be abstracting this, we could use any symbol like a star or a plus or a dot for times or all kinds of things that you can use to abstract this. But again, I think it's very helpful to think of this conceptually like these are properties about symmetries. So I'm using the composition symbol because that's what motivates this property. So that binary operation for our group needs to be, in order to be, for our set to be a group, its binary operation needs to be 1, associative, as we just mentioned, Two, there must be an identity element, and we have to say what that means in terms of the binary operation. So we can't say it does nothing because we're not talking about actual rearrangements. We're just talking about abstract properties of this set of symmetries. So we would say that the identity element, what makes an element an identity element is that it yields to all of the other elements when you compose them. So this idea of doing nothing has this property that if you do nothing and then you do a second thing, then you've just done the second thing. Or if you do a first thing and then you do nothing, that's still the same thing as just doing that first thing. So composing on the right or the left by an identity gives you just the other element. It's almost like two people at a door. They say, oh no, after you. Oh no, after you. The identity always yields to the other group element. And that's what you get as the result. And that's going to be the defining property for the identity. And it turns out that's strong enough to recover tons and tons of structure. So even though we're letting go of explicitly the identity function in a set of symmetries, it turns out that's still okay. And we'll still have a lot of very powerful results about groups, as we'll soon see. And then finally, inversion. So there has to exist an inverse. And intuitively, that means the symmetry that undoes something. But we need to define it, again, in this abstract sense. So we would say that an element in the group serves as the inverse for another element if composing them either way gives us the identity, right? Or I should say composing them both ways gives us the identity. And that is the strict abstract definition of a group. It's all three of those properties meant to model the properties of the symmetries we've talked about earlier. So I have a couple questions for you. And I'd like to just, if you're watching this video, it's worth just pausing for a moment to think about this. The first question is, well, it points out the existence of an identity in each group is a given, right? That's the second property. Every group must have an identity. So existence is given, but not uniqueness. That's not a given from our definition of a group. So what do you think about uniqueness? Do you think identities are sometimes unique, always unique, or never unique? And another way to phrase that to set yourself up well for proofs is that if you take two identity elements, possibly the same, possibly not, does their equality always follow for every group, sometimes follow, or never follow? So maybe think to a couple of the examples before about the shapes and movement and the Rubik's Cube. Are those identities unique? Think about what it means to be an identity for an element. Would they be unique? So that's worth pausing for a moment. And if I were here in person, I would ask you what you think, but I can't do that. So I will go on to answer this. Sorry. If you if you haven't paused it, I added another thing to think about and forgot. Right. So what happens if you compose the two identities? And that's a really good key idea. So let's develop this idea. Or if you still want to think about it, it's a perfect time to pause. So let's think about this idea here. So I have I1 composed with I2. Right? And what would the outcome of this be? And what can we argue the outcome would have to be? Well, if I go up a little bit and I think about what it means to be the identity, any identity has the property that if I compose it with any other group element, then I get that group element. So focusing on I2 is an identity. And if I let G represent I1, then because I2 acts as an identity, it is an identity, I'm just going to get I1, right? This is an identity. This is in any group, right? This just follows from the axiom or the definition of an identity and an existence. So here we have an identity I2, right? So I2 says, oh, no, it's you. It's definitely you. But at the same time, I1 is also an identity. So maybe switching colors here. This is also an identity. And so I1 insists, oh no, it's absolutely you. And we get I2 from that fact as well. We go back up to the definition here. This is I1 is an identity which insists that the outcome, right, is the other element. So if I were to compose any two identities, I would have to get both of them as a result, which means both would have to be the same. So from seemingly a less strong hypothesis, we're thinking, oh, we can have many identities. We only have to have an identity as existence. Well, no, it actually turns out that only stating that forces identities to be unique for every single group because of this reason, because of this property that identities have. So what do you think? Was that a much stronger statement than it appeared to be? Now going on to a second question. Maybe I should zoom out a little bit. There we go. Zoom in a little. Okay, so we just discussed uniqueness of identity elements in a group. What about inverse elements? Each inverse element is X. Oops, I need to fix that. Is X. Where is that? There we go. X as a way to undo another element. Must each inverse be the only group element that undoes a given element, right? So normally we have like, if we think of G as like a twisting the side of a Rubik's Cube type of thing, and then we were to think of G prime as untwisting, or if you like invertible matrices, you could use a -1 and use the inverse notation and think about how matrices are undoing each other to get the identity matrix. That's another good example of groups. It's the invertible matrices on a vector space. Then what this kind of undoes this G prime undoes G, and it does it in both ways. But if we had two things that undid an element, would they necessarily be the same, or could they be different in some cases? So this is another good time to pause the video and think about that. And if you were exploring whether or not it's possible to prove this, maybe you're hunting for a counterexample and how this can't be proven. Let's say G prime is an inverse of G for some element G in our group, and we also have G double prime acts as an inverse of G, and we get the identity as well, right? So could we argue that necessarily G prime and G double prime must be equal? Or is that impossible to argue? And could you come up with maybe a counterexample for when we have two different inverses for the same element? So again, good time to pause. All right, now I'll proceed. So how can we argue that these are in fact always the same, G prime and G double prime? Well, we have an identity element here, and I'd like to be able to compare them. And also we have this magic property that G prime and G disappear in pairs, or they can kind of pop into existence as well because they're the identity. And the same thing with the other case. So at first I was thinking, we can multiply both sides by the same thing, but actually I'd really like to just start with one and leverage that the other is equal. Maybe I'm a curmudgeon and I just want to get it done, but that's what I want to do. So I'm going to start with G prime, and I'm going to say that G prime is the same thing as G prime composed with the identity, because that's what the identity does. The identity has to exist in our group, so we let I represent that identity element. And then we have the identity is also equal to G composed with G double prime, because G double prime is also an inverse. If I look up at the group properties real quick, right here we have, boom, G double prime acts as an inverse, and so that's also the identity. We can write it both ways. So that's also the identity, and this is associative. So, the order matters. I can't just like rearrange the left to right order, but G prime, then G double prime can also be interpreted as G prime after G double prime. Oops, forgot to close the parentheses. Here we go. Right, so we have G prime, then G, and then G double prime, right? And again, this is the identity as well. And boom, there we go. Using all of those explanations to leverage ourselves from the left to the right. Well, I guess this side for you, this side for you. We have G prime and G double prime are necessarily equal because they're both inverses of G. And that also means that inverses are unique. Not just for, symmetries, the way we've described them, but for these abstract groups. So just with a couple of arguments, we've forced identities to be unique, and that inverses are unique to whichever element they are inverses for, which is pretty cool. And then as a little bonus, as a little corollary here, if I called G inverse the unique element, that, oops. Actually, the unique inverse, the unique inverse of G. If I call that, then I can also say that G inverse, which is the unique inverse of G inverse, must equal G. Right? I guess that's not a corollary. That's a proposition. But we can prove that using the uniqueness of inverses. So we can observe that G inverse composed with G inverse, that must be the identity because it's the inverse of G inverse. But also, G with G inverse must also be the identity because G inverse is the inverse of G. So because inverses are unique, this is a corollary. This is a corollary. Because inverses are unique, we can immediately claim that the inverse of the inverse is the regular element, just as it was true for invertible matrices. So it's a really nice idea, and it's also automatically true, well, after these proofs, for every single abstract group. So pretty nice. Moving on to some examples. I think we talked about these before, but I just thought I'd include them for fun. I think I already mentioned structures of the plane, but so I apologize if this is repetitive. But yeah, I did mention example the symmetries of the plane. This one's neat. So depending on how much symmetry your triangle has, you have a different symmetry group for your triangles. Isosceles triangles have one reflective symmetry that interchanges your two congruent sides, or the identity, right? Scalene triangles have no symmetry other than just the identity. And equilateral triangles have like this full maximal possible symmetry. They have 6 different symmetries. You have two two rotations, like a third of the way, 2/3 of the way, and then the identity, and you could think of that as 3/3 of the way, like a full rotation, which just puts everything back to where you started. And then you have three reflections as well, one for each of the three lines of symmetry, because you can think of equilateral triangles as isosceles triangles, but three different ways, based on the two congruent edges you're talking about. So that's pretty neat as well. And this is an exercise I will leave to you just because it's kind of fun to do. This is called a Cayley table. Sometimes people call it a multiplication table, but it means um, it means just like you would multiply two numbers, you would compose two symmetries. So this is partially filled out, but if I have the identity on the top and then the identity on the side, doing the identity and then the identity still has the identity. And if I were to take any two symmetries of an equilateral triangle and I were to compose them, I would get a resulting symmetry from that. And it would have to be one of the six symmetries of a triangle. So this lets us kind of parse out and figure out what happens to each of these symmetries when we combine them via composition. So just a little note, if you'd like to fill this out, these are the symmetries that would go first, and these are the symmetries that would go second, just to kind of keep the order there. And that's about it. The homework is on some of the abstract properties. So it's proving more abstract properties, in particular when groups are commutative, which is to say that not only are they associative, so you can combine them any way you like, but you can also switch the order, and that has a really intimate connection to inverses. In particular, I'll make a quick comment about this. If I were to think about the composition G1 after G2, I guess, it doesn't really matter. But if I wanted to talk about the inverse for this, I know that G1 and G2 both have inverses. And it's tempting to just say that this must be G1 inverse composed with G2 inverse. And this is incorrect. This is incorrect. And the reason it's incorrect, or an intuitive reason for why that's incorrect, is you can think about what you need to do in order to undo multiple steps. For example, if you wanted to undo the process of putting on your socks and then putting on your shoes, you cannot take off your socks first and then take off your shoes. And I love that because just the image of trying to take your socks off first is hilarious. Like you're pulling your socks down, and they won't budge because your shoes are on, preventing you from removing your socks. And so hopefully once you describe it that way, it's like, no, you don't start by undoing the first thing you did. You start by undoing the last thing you did, and then you work your way backwards. So this is wrong, and the right, oops, that's right, OneNote erases things when you scribble over them. The right thing to do is to invert the very last thing and then the very first thing. And so you've got to switch the order if you want to talk about the inverses. And we can show that this is the inverse. So let's look at what happens when we compose these. You might have seen this with matrices in linear algebra. So G2 inverse, G1 inverse. Okay, so I look at this composition, and again, this is associative, so I'm just going to drop the parentheses. I don't need them. G2 inverse, G1. So I look at all of these, and these two undo each other, because if I'm thinking left to right, even though function composition's right to left, but if I'm thinking left to right, if I do G2, if G2 is the last thing I did, and then and then I immediately undo the last thing I did, then they'll undo each other. So what I get is G1, then the identity, and then G1 inverse. Forgot inverse. And then the identity just can be absorbed into either of those. And then I got G1, G1 inverse, which is again the identity. So this always works. You're just undoing things in the opposite order so that from the back forward or from the outside in, you're peeling off the things that you finished with in the correct order to get to the identity. So there's a really neat connection between trying to change the order and commutativity. So I hope those statements and those hints help get you started on the homework. That's also, I think, all I have to say about group theory and symmetry. So I hope you enjoyed this. I hope it was helpful, and have a wonderful rest of your week.